Hello everyone, I'm pleased to welcome you today in the name of Siglent Technologies. My name is Patrick Gold and I'm Siglent Support and Application Manager for Europe. To sum it up in one sentence, I'm there for you if problems need to be solved. It doesn't matter whether you don't know how to approach an application or you're already measuring and not getting the right results. Today, I would like to discuss with you how you can ensure that the communication of your IoT system is stable. The point here is not that I explain you how to design a communication system or what therefore is required, but I want to show you some measurements and the related tools with which you can find problems. Because I assume that each of you has at least an idea of what to look for when you know that, for example, an antenna isn't matched to an amplifier. Much more important is how to figure it out. Therefore, we will go together through a typical communication chain, step by step. Based on this, I will show you which measurements and tools you can use to identify problems. The main purpose of this communication chain is to show the various points of interest. It neither covers everything, nor is everything you see here always there. And of course, communication usually works in two directions. So, let's start. Basically, it's always about getting data from A to B. Therefore, something will provide data, which has to be transported later. This can be the start code of a keyless car key, or just a value from a temperature sensor. When it comes to IoT, the biggest part is about wireless communication. But before we arrive there, some data is forwarded in some form from a CPU to a communication module. And here I would like to start. This is of course a range that falls out of stream here. We can call it the DC part. At this point, you need classic measurement devices such as oscilloscopes, multimeters, signal generators, laboratory power supplies, a lot of devices for many different tasks. Here, you usually try to build a power supply that is as efficient as possible and therefore battery lifetime saving. Also should the power supply be as low noise as possible. Otherwise, not only the analog data could be influenced, but this can also have a negative effect on the communication module itself. Within the DC part are a lot of different tasks for the test and measurement equipment. Usually one would like to take a look at the buses with the protocol analyzers or simply simulate the different sensor states with the signal generator. You see, this part contains a lot of basic stuff, but it's very underestimated. Especially a bad power supply is often a major problem for wireless communication. And it's usually considered as one of the last possible reasons for a problem. Since you have many different tasks here and want to build a reliable basis for your system, your tool should be flexible and precise enough to fulfill all your requirements. Back to our communication chain. From here on, there are huge differences between the individual systems. The reason for this lies in the big amount of communication protocols and the large selection of components with very different levels of integration. If you are designing a system that is planned to be manufactured in small numbers for a specific application, then you will probably use a finished module that has the entire interface, including antenna, already integrated on one circuit board. Or you're the one who designs such a model for integration. Then you have to keep an eye on the entire communication chain, from the data source up to the antenna. There are also many partly integrated solutions which are often used. For example, something as a ready-made Bluetooth module for something like a smartwatch. Such a module is mostly integrated, but has to be used with an external antenna to get out of the metal housing. Because we are talking about billions of different solutions for at least a similar amount of applications, I would like first to go roughly through the decision-making process that decides what you will design later. Because what you want and should test is mainly based on these decisions. First, we have to decide on a communication standard. If you want to integrate your device into a smart home, then choose Zigbee or Z-Wave. If your device has to work anywhere in the world, it might be LTE or Extended Coverage GSM for IoT devices. There's also a fair chance that your device needs multiple interfaces. There are three main factors which has to be determined: time to market, and what the product development as well as the final product may cost. These factors decide which components you can take for your project. Should you cover all functions in one module or focus on being cheap and compact? Usually you also have to figure out some individual problems and solve them. Something like the example I mentioned before, that you cannot build antennas into a metal housing. A suitable solution has to be found. Based on this, the design complexity is mostly determined. In order to be allowed to use a communication standard in the end, you have to get the corresponding certification for your device. Several tests have to be passed herefore, such as the occupied bandwidth or the adjacent channel power. Herefore, our spectrum analyzers offer ready-made measurements with which these signal properties can be easily checked. Of course, the topic EMC should also be not underestimated, especially when you use a device with a high-frequency DC-DC converter to be particularly efficient and also have antennas in your device. At this point, these antennas are a perfect way for the distortions to leave your device. All in all, in the end, it doesn't matter whether you don't get an approval because of a failed EMC or a failed communication standard test. If you don't recognize mistakes in time, it's possible that you have to take a step backwards, sometimes back to the choice of components. To avoid this, you should test and measure in every design step, especially when you're integrating new technologies with constantly changing requirements. Now that we figured out that each of you has probably completely different hardware at this point, let's take a look at the basic structure of a transmitter. At the front, there is always some type of transceiver that modulates the data according to the protocol and then forwards it to the amplifier. Then usually there's some kind of filter and, of course, an antenna. You will find these components in most systems in some way. When you're developing such a product, try to make as many test points as possible accessible, at least within the prototype. For example, you can create a second PCB with your antenna design or an optional SMA connector on a trace between two components. The goal is, of course, to be able to capture as many signals at as many points as possible. The antenna test is the first test which I want to show you. Probably also the test that almost nobody can avoid, regardless whether you develop the antennas yourself or buy them. The impedance matching must always be checked. Basically, it's about how good the antenna input impedance matches the output impedance of the signal source. Basically, how much energy is reflected. Conversely, you can then deduce how much energy the antenna is emitting. This can be done either with a spectrum analyzer with a reflection bridge or with a network analyzer. Here I would like to point out one thing. Nowadays, it hardly makes sense to buy a spectrum analyzer with a reflection bridge. A spectrum analyzer with integrated one-port network analyzer usually costs less and can do significantly more. For example, I can also obtain phase information and display my measurement results in the Smith chart. If you're new to Smith charts, don't worry about it. In the end, it's very simple. There are 50 ohms in the center, and if your result is on the left side, the real resistance is too high. If you're on the right side, it's too low. If your measurement results is above the center, you have too much inductance. If it's below, too much capacitance. It shows you quite easily how your compensation network should look like. One more thing. If you buy antennas or your own design is produced by some kind of PCB manufacturer, you should always have regular in-come inspections for your antennas. I had many customers who had very bad surprises with the deviation of the individual batches and had some product recalls. Therefore, try to keep in mind that antennas should be tested frequently. Testing a filter looks very similar. However, here we measure the passage and not the reflection. With the spectrum analyzer, we work with the tracking generator. With the network analyzer, we record S21. Here we can see a tripole filter, which is adapted to 435 MHz. We see a flat frequency response at the passband and steep slopes before the 3 dB points. So it's a nearly perfect filter. On the other side, we can see a little bit more on the network analyzer. You can also analyze the reflection at the same time and also see the S parameters in the Smith chart. An amplifier is a little bit more complicated. Here it's not only important to test the frequency response, but also evaluate the stability via different input amplitudes, supply voltage, and so on. Sometimes you can find completely unexpected effects in areas that are not actually in the foreground. For example, have a look at my measurement here. This amplifier is made to amplify at 2.4 GHz with 10 dB, which it does. But there's also an interesting peak at around 2 GHz. Actually, if you know that, you can filter it accordingly and it's no problem. But you have to find it first. Since I cannot go too much into detail here, please let me recommend you this video from my colleague Jason. He made a short video introduction to amplifier measurements here. If you want to have a first look into the topic, please find it on YouTube. For those of you who already have experience here, I have another recommendation for you afterwards. But now we come to the elephant in the room. The actual signal analysis. What does an analyzer have to bring with it? First of all, it has to support the needed modulation type. It must be able to process the necessary amount of data and must have, therefore, the necessary capabilities to handle the data. Furthermore, it must be able to obtain the relevant information and must be able to display it correctly. Please let me show you an example measurement. Here we see the analyzer of a 64 QAM signal. You can see that the recorded data is correctly assigned to the constellation diagram and also that the neighboring channels are not disturbed. It's not perfect, but with an error vector magnitude of 1.3%, it's quite good. The eye diagram also shows that the individual signals can be clearly distinguished from another. Here we have basically the same signal. We just have increased the level of the signal in front of the amplifier a little bit. Therefore, the amp is overdriven. You can see how the points no longer hit the constellation diagram and the error vector magnitude is increased. Also, the neighboring channels are now disturbed. If you're interested in this topic, please have a look at the corresponding YouTube video from the signal path. It not only shows a few wonderful example measurements, but also a teardown of our SVA, and it also explains you how it works in time. And once again, back to our communication chain. Now we could go through the whole thing again, and I could explain you again that an antenna has to be matched and so on. To skip that, I would like to tell you just a short overview how to make a complete receiver test. With a flexible signal source, you can make many different receiver tests. The most important ones are shown here. The receiver sensitivity is usually the starting point. The question is, can you capture the required signals? For a reasonable sensitivity test, you need a signal generator that can output signals that are small enough. Our RF generators offer a dynamic range from up to 20 dBm to minus 140 dBm. so you should be able to cover the most of the necessary range. If that's not enough, you can help yourself with a good attenuator. But the attenuation of interfering signals and the adjacent channels is also of crucial importance. Here you should have a two-tone generator and the option to add white noise to your signal. Generating IQ signals is a very basic requirement for such tests, but also a complex topic. We offer some standard signals in our SSG 5000 series, and the device offers the option to generate IQ signals without a connected PC. But the question is always, is there exactly the signal that you need for your test? If not, we also offer free software with which IQ signals can be generated flexibly. Different test environments, such as LabVIEW and MATLAB, offer of course the biggest flexibility. Here you can create any signal you want, but of course your generator must be able to play it. Please keep that in mind when you're looking for the regarding device. In the end, of course, I still have to test the device in the real world. For this, one factor is very important. Of course, to be able to find the problems. Otherwise you cannot solve them. You have to understand what's happening in the environment, and here I want to show you a very important tool. When we are in frequently used frequency ranges, we often don't have just one signal that we can receive at the same time. Think of the 2.4 GHz range with stuff like Wi-Fi, RFID, Bluetooth or Zigbee. There's a lot of going on here. It can happen that the signal which we are looking for cannot even be seen with a classic spectrum analyzer. If you mix these two signals here, you have only this peak as a hint for the missing signal, and I think it doesn't tell you too much about it. And this is exactly where we come to the real-time spectrum analyzers. These are powerful tools for telling signals apart. Here are the two signals from just now. But now you can clearly see what's going on here. See exactly both signals. Or think of pulse signals, or signals which do frequency hopping. These can only be viewed and evaluated with a real-time spectrum analyzer. So, if you make measurements within the IoT range, you should definitely have a look at such a device. Fortunately, we can offer you some interesting devices here. Let's come to a conclusion. As I mentioned in the beginning, a reliable base is essential for a good design. And therefore, it is important that you have reliable measurement technology that allows you to create a good design. For the DC part, but also especially for the communication part itself, flexibility in the measurement technology is very important. On the one hand, this is about ready-made measurements, but above all, being able to control the device in such a way that it can be adapted to every measurement you need in the future. Often, you can buy automated measurements for your devices afterwards, like the standard communication test which I mentioned before. With our devices you can even buy additional features like an VNA, but the bandwidth or the noise flow is determined by the hardware. That's why you should make sure that you have the bandwidth and the dynamics that you need. There's of course another factor at this point. The price has to be right. Depending on what you are developing in an IoT area, these are often small series or very tightly calculated devices. If the measurement technology is too expensive for such a project, and the product prices are therefore too high, in many cases you don't even need to go to the market. Therefore, IoT test and measurement technology must have a good price-performance ratio. And that's exactly the point where we see our strengths.